So again we begin with a new lecture. We will continue about X-ray diffraction as we were talking in the last lecture. So in the last class we were talking about the X-rays, basically the absorption edge in, of various materials, and how that absorption edge can be used in one, choosing appropriate filter to allow certain radiation to go through, certain radiation for you to use. And secondly, knowledge of absorption edge can also be useful in choosing appropriate radiation for a particular material. For example, for iron it is not appropriate to use copper, but you can use cobalt or chromium radiations. So now let us look at representation of X-ray diffraction in crystals. We will not look at the physics of X-ray diffraction in crystals because of lack of time, but if you are interested, you can go through any standard book on X-ray diffraction, such as X-ray diffraction by B.D. Cullity, or even there is a good interpretation of X-ray diffraction in Charles Kittle solid stress physics, which talks about diffraction, and essentially what happens in these cases, those cases, is that since X-rays are radiation, they have a wave vector. This wave vector is reciprocal of the wavelength. So the reciprocal is basically the reciprocal of length. Okay, so it has a unit which is meter inverse. So in order to deal with X-ray diffraction in that case, one also has to consider lattice in reciprocal terms. So use a reciprocal lattice vector instead of real lattice vectors, and then you can understand diffraction in the form of what we call as Lau equations or evolved sphere, which gives you a certain diffraction condition, which ultimately can be reduced to a scalar form which is called as Bragg's law. So we will straight away look at Bragg's law to interpret the X-ray diffraction in crystals. So we begin with Bragg's law. Now Bragg's law, basically you consider you have these parallel plane of atoms, so let us say this is a plane which is HKL. Okay. And the blue ones are the atoms. Okay. So these are the atoms. And hence, so this is HKL set of planes, and the interplanar spacing between these is D. D is the interplanar spacing. So D is interplanar spacing. So what you have here is you have a X-ray beam that comes from certain direction. Let us say let's put it in green. So let me first draw the normal to this. Okay. So we have X-ray beam which comes along this direction, and it gets diffracted in this direction. Okay. And this will be the outgoing beam, right. So this is I in, this is I out, and this is, so this is let us say transmitted beam. So let me just write it differently because transmitted, and this is let us say I out, this is the outgoing or diffracted beam. So we have a parallel beam coming from here as well, and this parallel beam comes in such a manner so that it hits, so sorry, kind of gone a little bit weird. So, I have to draw this in this fashion, so that it comes in. So, you have a parallel beam which comes like this, and then this also gets transmitted in this fashion, and this goes through the lattice in this form. Okay. The angle between, so this angle, the angle which it makes through with the plane. So, this is the plane here. So, this is the, if I draw this as yellow, let us say. So, this angle here is theta, right. This is also theta, and this is also theta, this is also theta, and this angle will be 90 minus theta, and this is also 90 minus theta. So, in some sense it looks like as if it is a reflection, okay, but it is not reflection, because reflection can occur at any angles, as we will see. It does not happen at any angle. Okay. So, now here if I do some geometry, now for diffraction to occur, basically the path difference must be equal to the integral multiples of wavelength. That is the condition for diffraction to occur, which comes from Thomas Young's experiment. Okay. So, if I now make a geometry like this, the path difference is sum of these, right. So, this is A, this is B, and this is C. So, the path difference I can write as is equal to AB plus BC. Okay. Now, by geometry I can say that this is 90 degrees, this is 90 degrees, this is theta, and this is also theta. So, this becomes d sin theta, and this also becomes d sin theta. So, this is basically 2d sin theta, and this 2d sin theta, the diffraction Bragg's law says that this must be equal to n lambda integral multiples of the wavelength. So, this is what is basically the Bragg's law. So, here n is defined as order of diffraction, theta is the Bragg angle or the diffraction angle, lambda is the wavelength. So, you can see here, since since you are using a, let us say if you are using a fixed lambda, if you are using a fixed lambda and you know from the knowledge of, so this is DHKL, all right. DHKL is not a random value. Okay. So, if you have 100 plane, if you have 110 plane, if you have 111 plane, and so on and so forth, they have specific values, right. Specific values will mean you have specific DHKLs. Specific DHKLs will mean you have specific theta values to satisfy this equation, because lambda is fixed. Okay. So, for a given value of n and lambda, your d sin theta product is, it has to be equal to n lambda divided by 2. So, which means if your d is fixed, theta is fixed. That means diffraction cannot occur at any random angle, it can only happen at those angles at which this equation is satisfied. So, that is why there is a fundamental difference between diffraction and reflection. Although it looks like reflection, it is not reflection, it is diffraction, which satisfy the Bragg's law, whereas reflection can occur at any angle. Secondly, reflection is only a surface effect, diffraction is a subsurface effect. The information from the surface, below the surface also comes out. Okay. So, the path difference must be equal to the integral multiples of wavelength, and theta in must be equal to theta out. And you can see the angle between the diffracted beam and the transmitted beam. What is this angle? This angle is 2 theta. The angle between the diffracted beam and the transmitted beam is 2 theta, corresponding to the Bragg angle. So, this is a typical Bragg's law essentially, and you can see now for crystals we have let us say a cubic crystal. So, cubic crystal, if you say for a cubic crystal, D will be equal to A divided by root of h square plus A square plus L square, all right. So, n lambda will be equal to 2 into A divided by square root of into sin theta. So, you can see that your theta will depend only on square root of h square plus A square plus L square. So, that is how you index your planes. So, when you go from various HKL values, so you start from 1 0 0, your h square plus k square plus L square will be equal to 1. What is the next value for h square plus k square plus L square? That is 4. So, this will be theta 1, this will be theta 2, and as you go to what is the next one? 1 1 1, this will give you value of 3, this will occur a value 3. So, this will be the, so for this h square plus k square plus L square is the smallest, theta 1 will be the, and this you can see the reciprocal, right. So, basically you can see that sin theta is proportional to, right. So, theta 1 is the smallest and it increases, right. So, as you now what is happening to D spacing? The D spacing is decreasing. So, this is decreasing, your theta is increasing. So, theta is increasing and D is decreasing. So, 1 1 1, you can go to now 2 0 0, that will give you 4 theta 4, and then you go to 2 1 0, that will give you 5 theta 5, and so on and so forth. So, basically when you look at the X-ray diffraction for a cubic crystal, at least when you look at the X-ray diffraction peaks, they go in the order of increasing values of h square plus k square plus L square as a function of theta. So, as theta increases, h square plus k square plus L square increases. Now, next thing I would like to come upon is what is the significance of, in the equation n lambda is equal to 2d sin theta, what is the significance of this factor n, which we said it was order of diffraction. In some cases they also called as order of reflection. Okay, reflection is a misnomer, but it is used very frequently. Okay. Now, what it means basically is that let us say if you have 1 0 0 plane, for 1 0 0 plane imagine n is equal to 1, then this becomes n is equal to 2 d 1 0 0 sin theta 1. Okay. Fine. Now, what does d 1 0 0 mean? Now, if you want to look at d 2 0 0 now, so this will mean again we take n is equal to 1. So, this will become 2 d 2 0 0 sin theta 2. What is d 2 0 0? It is nothing but d 1 0 0 divided by 2, because d 1 0 0 is a divided by square root of 1 plus 0 plus 0, and d 2 0 0 is a divided by square root of 4 plus 0 plus 0. Okay. So, this is a, this is right. So, by you can see that d 2 0 0 is half of d 1 0 0. So, this becomes 2 lambda is equal to 2 d 1 0 0 sin theta 2. So, basically it means a 2 0 0 peak is the diffraction peak from 2 0 0 plane is nothing but second order 1 0 0 reflection or diffraction peak. So, when you have these diffraction peaks, you will have diffraction peaks in modern machines like these, so on and so forth. This is intensity, this is 2 theta. So, let us say if this is 100, this is, I am not drawing other peaks, this will be 200, this is 300, this is 400. You can call this as first order 100, this as first order 200, this as first order 300, this as first order 400, or alternatively you can say this is first order 100, this is second order 100, this is third order 1000, and this is fourth order 100. That is the significance of n. So, this n, which is called as order of diffraction, is meaningful in this manner. So, this is nothing but n is equal to 1 for 100, this is n is equal to 2 for 100, this is n is equal to 3 for 100 reflection, okay, and this is n is equal to 4 for 100 reflection. Okay. Basically, the order of reflection, the same peak can give you, same plane can give you diffraction peaks at different angles. So, there may be no atom sitting at 100, 200, 300 or 400, it is just that the wavelength is now diffracting in such a manner, so that first it was lambda, then it became 2 lambda, then it became 3 lambda, then it became 4 lambda. Okay. So, it is as if in the first case it would be in this fashion. Okay. So, this was 1 lambda, this is lambda, this is lambda. Okay. In the second case it became, this was 2 lambda, 2 lambda. It is as if you have a plane sitting here, because if you had a plane sitting here, this would be lambda, this would be lambda. So, let us say this is first set of planes, you might have a plane here sitting here, let us say it may or may not be sitting, you may or may not have atoms. So, let us say this is 100, this is 200, this is so they are all HKL planes, but it is not right to draw them in this fashion. So, if you say that this is 100 and this is 100, then the middle of it will be 200, then you can also define this as 200. Okay. So, let us not talk about 200 at all, let us just talk about the 100. Now, if you have incoming beam in this fashion, let me use a different color, this is incoming beam, this is outgoing beam. And this is, let us say, the other beam that is coming parallel to this. This is, let us say, the other one which is going parallel to it. This is the path difference. The path difference is this and that. If this was lambda, okay, then the path difference is lambda, okay, 2 lambda. All right. So, this is 2 lambda. 2d sin theta, basically it is, in this case it is the path difference is 2d sin theta, and if this is equal to lambda, so which means this is lambda by 2, this is lambda by 2, then this is 1 lambda. Okay. Now, if you had a plane sitting somewhere here, let us say, then what would be the path difference be? If I now draw a hypothetical beam coming here, then what would this path difference be? This would be lambda by 4. What would the path difference be for that? It is destructive interference. So, which means for a first order 100, there could be no second order 200, or there could be no 200 reflection, because 200 plane does not diffract at that position. For that to occur, now beam has to bend, okay, it has to change the angle in such a manner so that the path difference changes. So, now when the path difference has changed, let us say the beam has bent in this fashion now, so that your now Now, when you draw the, this is now, since the angle has increased, the path length has increased, let us say this is now equal to lambda, this is now equal to lambda. Okay. So, your 2d sin theta has now become equal to 2 lambda, all right. What it makes, so this is d 100. If you had a plane in between, and let us say the beam, you draw another beam in between, the path difference for this would be now half of that. You can just draw a perpendicular here, this would be half, this would be lambda, this would be lambda by 2, this would be lambda by 2. So, you can say that for 100 it is second order diffraction, but for 200 it is first order diffraction. This is what it means. Okay. Similarly, you can draw for third order, fourth order, the multiples will get increasing, 3 lambda, 4 lambda. So, when the path difference between successive 100 plane is 4 lambda, which means you will have fourth order diffraction. So, even whether you have plane or not, if you have a plane, if you have really a physical plane present, then the position of atom will determine whether diffraction will take place or not, that we will discuss later on. But if you did not have those effects taking place, then you will have a fourth order 100 if the path difference is 4 lambda.
And we will get the reflection
at different angle, because now you have, now the theta is increased, right. So, that is why it comes on the higher angle, because the path difference has to increase. Okay. So, this theta is lower, this is lower, and this is smaller angles, and this is at higher angles. Basically, you can say with respect to this. Okay. So, with respect to the normal, you can say not this, but with respect to that, the normal, the beam has to flatten out, okay, or rather other way around actually. This should be lower theta. So, this will give you in fact, so here you will have higher path difference as compared to the previous case. So, this will have higher path difference, and this will have lower path difference. Okay. All right. So, I hope this is clear now. Now, when you want to use, when you want to analyze crystals using diffraction methods, there are, depending upon the type of crystal, we use different methods. So, if you have single crystals generally do not give you multiple freedom of orientation, because the faces of crystals are fixed. As a result, in single crystals we generally use variable wavelength. So that you have multiple peaks coming out of the sample at various, so you want to get more data to analyze it. So, variable wavelengths are used. This method is called as Lauer method. Okay. There is another method for single crystal, which is called as rotating crystal method. In that method again, the wavelength is however not fixed, wavelength is fixed. So, it is a fixed lambda, but crystal rotates. Okay. So, you have a crystal which undergoes rotation, and this is the incoming beam of fixed lambda. However, in case of polycrystals, let us say powder specimens where every plane is randomly oriented in space. So, you have every possible orientation available to the incoming X-ray beam. See, the problem with single crystals is that if I have a single crystal specimen, then let us say my incoming beam is, this is my incoming beam, and there are only a very few planes which may be appropriately oriented with respect to the incoming beam, especially if your sample orientation is fixed. Because remember, you have to follow n lambda is equal to 2d sin theta. If your lambda is fixed, then the only two things are d and theta which are dependent upon each other. right. So, orientation of particular plane with a particular d spacing will not guarantee whether you will have Bragg's law satisfied or not. So, as a result you need to increase your, you need to change lambda so that a particular plane will diffract, okay. And there is no guarantee that all the planes will diffract because there are very few orientations available. So, that is why you need to vary lambda. If you do not want to vary lambda, then you need to create more opportunities for theta, which means you need to rotate the crystal, okay, for diffraction to occur so that you can get some data out of it. However, in case of powder specimens, if you have bunch of powder, one HKL might be like this, another HKL might be like this, another HKL could be this, another HKL could be this, another HKL could be this. So, you can have multiple orientation of HKLs. So, when the beam comes, it will always find a peak it will always find some plane for diffraction which is oriented perfectly according to Bragg's law. So, for powder specimens we generally used fixed wavelength, okay. So, lambda is fixed and angle may or may not be changed. The sample may remain stationary or sample may rotate. Then, okay, by and large we can keep it fixed, but we need to change the detector position. So, if this is your incoming X-ray beam, if this is your sample, if this is your detector, so this is in, this is out. If the sample is single crystal, then you need to, if you move the detector, so detector will move in this direction, normally your beam is fixed, you will not get much diffraction, only from those planes which are favorably oriented, not from anything else. Then because you need to satisfy this 2 theta geometry. If 2 theta, remember for diffraction to occur you have to have for a given plane theta in, theta out as equal. If this geometry is not maintained, then you will not get diffraction, all right. So, in case of powder specimen, since there are multiple orientation present all over the place, so you will have diffraction taking place. All you need to do is that you can keep the X-ray beam fixed, you can keep even your sample fixed, you can just move the detector. Whereas, in case of single crystals you may have to move the sample, you may have to move the incoming beam as well to get the maximum diffractions occur, maximum diffraction possibility. So, this is what these are the 3 methods which we use for diffraction in crystals. The Laue method for which has variable wavelengths for single crystals, rotating crystal method with fixed wavelength for again for single crystals, then we use powder method for the powdered or polycrystalline specimens. So, this is for polycrystalline specimens. If you are not clear about what polycrystalline and single crystal specimen are, I will explain that a little bit in the next class. Okay, so, in the next class we will again discuss X-ray diffraction, its utility to crystals, and give you certain examples before we move on to finally the defects in the materials. Okay.